Number 5 is a complex fraction. A fraction within a fraction. There's a couple of ways to work that. One way, and I think this is probably how we did it earlier in class, is we consider this a division bar, and we combine those fractions, divided by, combine those fractions. And then we would flip and multiply. So then it became kind of like the O problems we just talked about. But I want to show you a quicker way to do this that will help you work this, I hope. And that is, think of this as being 4 over 1. Look at each denominator and find the LCD of all fractions involved. So every fraction, the 1, x, 8, and 4, would all go into 8x. You need the 8 for 4 and 8 to fit into it, and you need an x for that to fit. So 8x is the LCD of all fractions involved. So if I times the numerator of this complex fraction by 8x and the denominator by 8x, I'm keeping the balance on the big fraction, right? I'm allowed to do that. But what that does for me is it means now when I distribute that, because we are multiplying, so that will distribute, that it will wipe out every fraction. And so it takes care of all the denominators, kind of like the equations when we do the same thing to each side times somebody else. So same idea here. 8x times 4 makes 32x. 8x times 2 over x. Now the reason we had to have the x there is because we have this denominator that needs to cancel out. So that would cancel and just leave 16. No fractions left, right? That's the whole idea of LCD, wiping out the fractions. Same thing for the denominator. 8x times x over 4, the 4 and the 8 will be diagonal, leaving a 2. X times 2x is 2x squared. Use that 8x again, we're distributing it. 8x times 1 over 8, the 8's cancel, and you have 1 times x, or x. So that's probably a quicker way of explaining a complex fraction. It's times by the LCD, every denominator times the LCD on top and bottom, and then distribute it into every term. Then you won't have a fraction within a fraction. It takes out the complex part of it. Now listen, this is what I really want to warn you about. In general, on the test, it is not forgiving. There's no multiple choice. There's no partial credit on multiple choice tests. So every little detail has to be just right. And one of the details may be, if you look down at the answer key, this may be a choice, but that doesn't necessarily mean it's right. It's because it's one of the choices, although it's not in this case. But the reason it's not a choice even is because it does factor and reduce. You can, and like I said on the last problem, always try to factor and reduce if possible. So there's a GCF on the top of 16. And what's the GCF of the denominator?
X.
X. And look, it leaves 2x plus 1. Now we get that common match, which we're allowed now to cancel because it's in factored form for the final answer of 16 over x, which is a choice. But what I wanted to say is, even if it would have been a choice in that formula form, you couldn't have used that. It has to be in final reduced form to count. Okay, number 6. The next few questions deal with the exponent rules. Remember, back in chapter R, we had all those exponent rules. Well, the next few problems kind of pack all those rules into just a few problems to try to really make you think about how the rules work together. When we learned these, we kind of took it easier on you and said, like, x2 times x3 is x5. You know, the rule that says if you multiply like bases, you add the exponents. We had the rule that said an exponent to an exponent multiplied. We had a rule that said if you have a fraction to a negative exponent, it flips the fraction and makes the exponent positive. So flipping a fraction changes the sign of the exponent. We're going to use that. What else? Or if you just have, say, an x to the negative 3 over y to the negative 4, those can kind of switch places. Taking y to the negative 4 to the top makes it y to the 4. X to the negative 3 to the bottom makes it x to the positive 3. So moving things around, even individually in a fraction, changes the sign of those exponents. Okay, I think that's what we need to know then to go into number 6 and 7. Number 6 is actually all arithmetic. You could do this on your calculator if you're careful about how you type it in. But anyway, I'd rather you know your exponent rules, that because you have a negative exponent, if you flip that fraction, it'll make that exponent positive. So flipping the fraction makes it negative 125 over 64. It's still a negative number. It's just the exponents that are getting affected. All right, so good. Flipping the fraction, now it's positive 2/3. 2/3 powered means it's a cube root, that's the root, raised to the second power. The denominator is the root. So notice both of these are perfect cubes, so we'll be able to take a cube root, and we can take cube roots of negatives. If this would have been to an even power, an even root, a negative to an even root, like a square root of a negative, we said not real, okay? But because it's a cube root, we can do a negative. It will be negative 5/4. Right, still negative. Negative 5/4 times negative 5/4 times negative 5/4 is negative 125/64. But not only do we do the cube root, but then we square the answer, so the negative kind of disappears now anyway. The negative squared makes that positive 25/16, final answer. Okay, number 7. Now we're in more algebra mode, so our calculator wouldn't help us here anyway. So we're going to apply a lot of the rules we just talked about, and there's some different orders you could apply these rules. Like you may prefer to go ahead and move within this parenthesis, that negative exponent, move it down, makes it positive. That's an option. I'm not going to though. I'm going to go ahead and apply the power rule, which says an exponent to an exponent multiplies. So negative 5/6 times, and that's really 2/1, would reduce to negative 5/3. So it's going to be b to the negative 5/3. Into the negative 7/4 raised to the second. Exponents to exponents multiply. So negative 7/4 times 2, let's just check that out. Negative 7/4 times 2/1, you could reduce it down, it'd be negative 7/2. Times between there. Okay, over here we're going to take an n to the 1/3 raised to the negative 3. That's the power rule. A power to a power multiplies. So 1/3 times negative 3, the negative 3 is over 1, cancels out the 3's, it's negative 1. b to the 1/7 to the negative 3rd multiplies, makes that negative 3/7. All right, now if you wanted to, and I do, I have all these negative exponents everywhere. Every exponent is negative. I'm going to move their position so I'll have positive numbers to work with. I think it's easier. So this n, I'm going to move it up, makes it a positive 7/2. b to the 5/3 moves down. n to the negative 1 moves down. And b to the negative 3/7 moves up. So every negative exponent, move its position, changes the sign of the exponent. So here's what we've got at this point. So now it will reduce, and I don't think I mentioned this rule earlier, but the reducing comes from the quotient rule, which means if you're dividing like bases, you subtract the exponents. So the b will reduce 3/7 minus 5/3. That really slows me down. I don't know what 3/7 minus 5/3 is without getting a like denominator of 21. 7 into 21 is 3. 3 times 3 is 9. 5 into 3 into 21 is 7. 7 times 5 is 35. And then that reduces or subtracts to be negative 26 over 21. So b is to the negative 26 over 21 power. When you use the quotient rule, top minus bottom, it's the answer as it would appear in the numerator. I will need to move that now to make it positive. But subtracting top minus bottom, that is the answer as it appears in the top. 7, now the n, 7/2 minus 1. I can make a like denominator of 2, make that 2 over 2. Subtracts to be 5 over 2. So that's n to the 5 over 2. Because this negative exponent